Welcome to The Explainer. Today we're going to tackle one of those questions that seems super simple on the surface, but when you dig into it, well, it unlocks the secrets of pretty much everything, from the satellites over our heads to planets orbiting distant stars. It's a question that people have been asking for thousands of years.
Okay, let's just dive right in. We all know how gravity works, right? You drop something, it falls. It's what keeps us stuck to the planet. So if that force is constantly pulling on this massive rock in the sky, why hasn't it crashed into the Earth after, 4 billion years? It feels like it just doesn't add up.
And this wasn't just a puzzle for us. This exact paradox had some of the greatest minds in history totally stumped. To solve it, someone had to realize that the rules up in the heavens were the exact same rules that govern things down here on Earth.
And the guy who finally cracked it? None other than Isaac Newton. The story goes that it all started when he saw an apple fall from a tree. But his real stroke of genius was thinking, hey, what if the force pulling that apple down is the exact same force that's holding the moon up? The only difference, he figured, had to be speed and distance. So how did he connect an apple to the moon? Well, it all comes down to one of the most brilliant and honestly simple thought experiments in the history of science. It's the key to understanding what an orbit really is. Okay, so picture this. You've got a cannon on a mountain so incredibly high that it's above all the air. Fire a cannonball, and as you see here, it travels a bit and then falls back to Earth. No surprise there. Fire it faster, and it goes farther before it lands. But what if you could fire it with the perfect sideways speed? So fast that as gravity pulls it down, the Earth's surface curves away underneath it at the exact same rate. What happens then? Well, it just keeps falling and falling and falling, but it constantly misses the ground. That, right there, is an orbit.
So here's the big takeaway, the really mind-bending part. The moon, the International Space Station, every satellite up there, they're all in a constant state of freefall. Orbiting isn't floating in zero gravity, it's falling so fast sideways that you just keep missing the planet below you.
But here's the thing, this doesn't just happen by chance. Staying in orbit requires this incredibly precise, delicate balancing act between wanting to fly off into space and being pulled down by gravity. And that magic speed has a name, it's called orbital velocity. It's the speed you need to hit so that the curve of your fall perfectly matches the curve of the Earth. For something like the space station in low Earth orbit, that speed is an unbelievable 7.9 kilometers, that's about 5 miles, every single second. I mean, that's fast enough to circle the entire globe in about an hour and a half.
Yeah, you can really think of it like a constant tug of war. Every object in orbit has momentum, which is trying to fling it off in a straight line out into space. At the same time, gravity is constantly yanking it back towards the planet. If you're too slow, gravity wins, and you spiral in. Too fast, and you overcome gravity and escape forever. You have to get it just right.
So, okay, we have this perfect balance, but does it actually last forever? Well, for things orbiting close to us, like our satellites, there's a sneaky little force that comes into play and slowly starts to mess things up.
We tend to think of space as being completely empty, a perfect vacuum. But it's not really. Even hundreds of kilometers up, there are still these tiny stray particles from Earth's atmosphere. And when you're moving at 5 miles a second, hitting even a few of those molecules creates friction or drag that slowly but surely robs you of your speed.
And believe me, the effect of this drag is huge. It's all about altitude. Look at these numbers. If you're orbiting way up at 800 kilometers, you might stay there for 200 years. But drop down to just 200 kilometers, where the atmosphere is just a tiny bit thicker, and your orbit will decay so fast you'll burn up in the atmosphere in about a week.
Okay, so all this talk about orbits decaying brings us full circle, right back to the moon. If even our high-tech satellites can't stay up forever, what's the deal with our moon?
I mean, it's been up there for billions of years. Surely some force, however tiny, should have caused it to spiral in by now. Logically, it just has to be getting closer, doesn't it?
Well, thanks to some nifty reflectors the Apollo astronauts left on the surface, scientists have been able to measure the change in the moon's distance with incredible accuracy. And this is the number they found.
Yeah, you're reading that right. In a completely mind-boggling twist, the moon is not falling towards us. It's actually escaping. Every single year, it gets about 3.8 centimeters further away. That's about the same length as your thumbnail.
So what in the world is going on? The reason is actually something we see every day, our ocean tides. Okay, stick with me here. The moon's gravity pulls on Earth's oceans, right? That creates a bulge of water. But And here's the key part, the Earth spins much faster than the Moon orbits, so that spinning Earth drags the tidal bulge slightly ahead of the Moon, and that bulge of water has its own gravity, giving the Moon a constant, tiny little tug forward. It's like a booster, and over billions of years, it has slowly pushed the Moon into a higher and higher orbit.
Okay, so let's zoom out. From Newton's cannonball, to satellites burning up in the atmosphere, to our moon slowly escaping, what's the big lesson here in this incredible cosmic dance?
All right, let's recap the big ideas. First, the moon is falling. It's just moving so fast sideways that it's constantly missing us. Second, we've seen that an orbit isn't some static, peaceful state. It's a dynamic, fragile balancing act between momentum and gravity. And finally, that balance isn't permanent. Forces like drag can make orbits decay, while other things, like our own tides, can actually give an orbit a boost and push things farther away.
And look, understanding this stuff isn't just for astronomers. It's what makes GPS, weather forecasting, and basically our entire modern world possible. But as we keep launching thousands and thousands more satellites up there, it leaves us with one last, pretty important question. In this incredibly delicate cosmic dance, who's in charge of making sure nobody steps on anyone else's toes?